Okay, so we're going to look at this first one. We're going to say, how does an air mattress protect a stunt person landing on the ground after a stunt? So if we kind of look at two situations, one where the person hits the ground directly and one where a person hits the air mattress, we kind of have the same initial momentum and the same final momentum. At each case, we can assume that they fell from the same height, which means that they had the same potential energy, which was then converted to the same kinetic energy, which means they're really hitting the ground at the same speed. And then when they finish hitting the ground, they have a velocity of 0. So if we say, hey, our change in momentum is our mass times our change in velocity, both cases have the same change in momentum. They had the same amount of energy, so they lost the same amount of energy. They had the same momentum change. So what we're really looking at is this idea that we had a change in momentum. We said that this equation, this mass times change in velocity, can satisfy our change in momentum equation. But we also know that we have this force times change in time equation. So if we look at this situation, well, we know we've probably been on a mattress before, hopefully. Not even an air mattress, just a regular mattress. But we know those are kind of squishy, so these have a little bit more give to them. So if you were going to land on here, it would take you more time to kind of come to rest than if you had hit the ground directly. That would be kind of a hard fall. You'd hit the ground, it doesn't have a lot of give to it. But this mattress has a lot of give to it, so it takes more time for the person to come to rest when they have the mattress. So we can say, okay, well, this delta t term for the mattress is pretty big, which means if we need the same change in momentum, the force can be kind of small. I didn't do a good job drawing that small. But so we're saying, hey, they're going to feel less force because it's spread out over a longer period of time. So it lengthens the stopping time and reduces the force. All right, with this one, we say a person of mass 60 kilograms sliding along level ice at a speed of 3 meters per second. So 60 at 3 meters per second, just going to get our picture drawn. Collides with the second person who is initially at rest. Assume the friction is negligible. If the two people hold onto each other and their common final speed after colliding is 2 meters per second, the mass of the person is something. So then they're going 2 meters per second. All right, so we just need to figure out what is the mass of this smaller person. Well, I guess we don't know that they're smaller. I just kind of envision them being smaller. The second person. Okay, so let's set up a situation. We have before and we have after. This is how we like to kind of set up, think about this collision as what happened before the collision, what happened after the collision. So we have person 1, I'll just call them M1, is equal to 60 kilograms. M2 is equal to an unknown amount of kilograms. So let's think about the initial momentum in our system. We have a person, 60 kilograms, moving 3 meters per second. We can say P1 initial is equal to M times V, 60 times 3, so 180 kilogram meters per second. And this person's momentum, even though we don't know their mass, we know that it's 0 because they're not moving. Which means the total initial momentum in our system is just going to be 180 kilogram meters per second. Which means that our total final momentum has to be 180 kilogram meters per second because momentum is conserved. Then we also know that these two people, they come together. They are moving with the same velocity at the end, so they stick. Which means if we were going to do this, we can actually treat this final object as one object with mass m1 plus m2 moving at a common velocity. Maybe I'll call it v final. So we know m1 is 60. Oops. So this is 60. m2 is what we want to find, and we know that their common final velocity is 2 meters per second. And we can set that equal to 180. So we can say 180 equals 60 plus m2 times 2, divide through by 2, we get 90 equals 60 plus m2, and we say m2 is equal to 30 kilograms. All right, so that's kind of our process for momentum. All right, with this question, this is one that we did not like on the momentum quiz that we took, so I put it back on here just to kind of get the idea across. But what we have is a 5 kilogram ball initially rests at the edge of a 2 meter long, 1.2 meter high frictionless table as shown above. A hard plastic cube of mass 0.5 kilograms slides across the table at a speed of 26 meters per second and strikes the ball, causing the ball to leave the table in the direction in which the cube was moving. The figure below shows a graph of the force exerted on the ball by the cube as a function of time. So on the ball by the cube. All right, so the first thing we're looking at is determine the total impulse given to the ball. We know that this impulse is really just kind of fancy talk for change in momentum. And this impulse, this change in momentum, can be found by finding the area under our force versus time graph. The area under our force versus time graph. So all we have to do is find that area. So we have two triangles with an area of 1/2. The base looks like 4 times 10 to the negative third. Right, that's our little units on this. And then our height is going to be 2 times 10 to the third. And we have two of those triangles. So 2 1/2 base times heights. That takes care of those. Plus a rectangle of base 2 times 10 to the negative third with a height of 2 times 10 to the third. All right, so then we can figure that out. These are all just going to cancel each other. It's 4 plus 2 1/2, let's cancel. 4 times 2, 6, or 8, just kidding. 8, 12. Change in momentum is going to be 12 kilogram meters per second. So the impulse is going to be 12 kilogram meters per second. That's our total area. All right, determine the horizontal velocity of the ball immediately after the collision. So what we're looking at here is kind of a situation where we can define our system the way that we want it. So we're going to say, hey, like impulse, the change in momentum is happening to the ball. So what we can say is like, within just the ball's point of view, the momentum of the ball is not conserved, right? If we treat the system, so let's define the system as just the ball, we can set up a situation where we say, well, before the collision, we had no momentum. And then after, we can say, well, the ball itself does have momentum. So you can say, well, this P final ball, we said is equal to 12 kilogram meters per second. We said, well, it has this change in momentum. So this is kind of like when we had the energy situations where work was done on our system. In this case, we have this impulse done on our system. So if we're going to set up a conservation of momentum equation, we can say, well, we have this P initial plus the impulse plus this change in momentum, right? This momentum was added to our system equals our final momentum. And we said, well, the change in momentum is going to be 12. So that's how we got to this idea that the final momentum of the ball is just going to be 12 kilogram meters per second. That's change in momentum. That's how much impulse was done on our system. So we know that its final momentum is 12, which means that the 12 is equal to its mass times its velocity final. 12 equals 5 times Vf. So Vf has to equal, what is that, 2.4, I think? 2.4 meters per second? Yeah. And then determine the speed for the cube immediately after the collision. So in this case, let's kind of revisit the system, except for this time, let's redefine our system. Let's call our system the ball and the cube, kind of where all the momentum is conserved. So we have two objects in our system. We have the ball and we have the cube. And let's try to just fill it out like we usually do. So, okay, with the ball, the initial momentum we said was 0. And for the cube, the initial momentum is just going to be 0.5 times 26, m times v. So it's going to be 13 kilogram meters per second. So half of 26 is 13, which means the total momentum in our system is 13 kilogram meters per second, which means that our total final momentum has to be 13 kilogram meters per second. We said that the final momentum of the ball was 12. So that means that the final momentum of the cube, which we don't know, 12 plus p final cube has to equal 13, which means my final momentum of the cube is just going to have to be 1 kilogram meters per second. We'll also notice that this is positive, so it's a positive 1 kilogram meters per second. So if we want to find the speed of the cube, we can say, well, momentum is equal to m times v. The momentum was 1, the mass is 0.5, which means the velocity final of the cube has to equal 2 meters per second. 2 meters per second, and this is happening in the positive direction. So it's moving to the right because we found a positive final momentum for that. Remember, momentum has a sign to it. If it was negative, that would mean it would be moving to the left, but it's in the direction that we defined as positive, to the right. All right, with this one, a 2 kilogram block on a horizontal surface is attached to a horizontal spring. So it looks kind of like this old situation where it's moving back and forth. Of negligible mass. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface. The block is released from rest after the spring is stretched, such that the block spring system experiences simple harmonic motion. So we are going to say, okay, let's fully stretch the spring. So fully stretched, let's just call this equilibrium. And then we let it go. So we start, hey, we have no velocity. This stretches at a max. Yeah, okay. Where was I shown the graph. Block is released from rest. Simple harmonic motion. I shown the graph that represents the block's velocity as a function of time. How could a student use the known information and the graph to determine the magnitude of the change in spring potential energy of the system from the release point of the block to the moment when the spring's potential energy is 0? Okay, so what we're looking at is a case. We want to know, how can we figure out this spring potential energy? So let's kind of do an LOL diagram situation. Even though we're dealing with simple harmonic motion, let's think about our two situations in our LOL diagram. First, we're going to look at this situation like it tells us in our problem. We want to know when the spring potential energy is maximum to when it's 0. So at the very beginning, when we have this maximum stretch, all of our energy is equal to the spring potential energy. And then we want to find a spot where all of the energy is the kinetic energy. So what we can say is, well, our total energy in our system is always equal to the spring potential energy and the kinetic energy, and we're kind of isolating. We're finding situations, or it's asking us to look at situations where we have all spring potential energy and no kinetic because it's not moving in the beginning, and situations where the total energy is tied up in kinetic energy because we're at a spot where x is equal to 0 and we have no stretch. So what we can say is that these moments, maybe I'll even label them A and B, at moments A and B, we have a unique situation where the total energy is tied up in one form of energy. So we can say the spring potential energy at A is going to equal the kinetic energy at B. So we kind of have this unique situation. So what that tells us is, well, also we can see going from A to B, our change in spring potential energy is kind of its maximum. That's what we're looking for. We're saying, hey, what's our spring, when our spring potential energy goes from its maximum to 0, that's what we're looking at. So we're looking at A to B. So what we need to find really is, if we want to find this change in spring potential from thing at A to 0, right, because it's 0 here, we can just find the change in kinetic energy from A to B. So that really just tells us, hey, we start with K initial at A is 0, K final at B is equal to some value. If we can find the maximum value of kinetic energy, then we can find the maximum value of spring potential energy, and then we're good to go. So we just need to find a situation where the kinetic energy will be maximum, and that happens at 2 seconds. We have a maximum velocity there, that's what we represent as B. So we have this maximum velocity, and then we can just use K equals 1/2 mv squared to find the kinetic energy. So that'll tell us a situation where that'll be able to tell us the magnitude, the change in spring potential energy from the release point to the moment where the spring's potential energy is 0. All right, I think last one, yeah. So a student sets an object attached to a spring into oscillatory motion and uses a position sensor to record the displacement of the object from equilibrium as a function of time. A portion of the recorded data is shown in the figure below. The frequency of oscillation is most nearly, All right, so a little reminder, we said frequency is equal to 1 over the period. The frequency is going to represent how many cycles we have each second. Whereas the period, what we're more used to, that's going to represent how many seconds a cycle takes, so seconds per cycle. So what we can say is, well, let's just figure out the period and then use this equation that tells us the frequency is equal to the inverse of the period, because period is really nice and easy to find from our graph. So in this case, we're looking for one complete, like there and back again. So this kind of looks like a maximum. So let's go from a maximum to the other, the same maximum. So we go, okay, we're going away from our maximum. So that's like half the cycle. And then going back to our maximum, that looks like the other half of our cycle. So it looks like our period, it takes us 0.5 seconds, 0.7 minus 0.2, it's 0.5 seconds to do one complete there and back again, one complete cycle. So, okay, we can say our frequency, or sorry, our period is equal to 0.5 seconds per one cycle. So then if we want to find our frequency, we can just say, well, our frequency is one cycle every 0.5 seconds. So that means if we say, hey, 0.5 is just equal to 1/2, we're really just flipping 1/2. We can say our frequency is going to be 2 hertz. And that seems, yeah, that seems pretty good. All right, cool.